Okay, thank you, everyone. So I'm happy to have opportunity to present my recent work on the GPU RDMA support in the Linux kernel using Dma-Buff. So here's the agenda. At the beginning, I will talk a little bit about the GPU RDMA itself, then followed by some introduction of the Dma-Buff, what it is and how it is used. And then give some example of how use Dma-Buff for GPU RDMA, followed by the demonstration of how to implement this support in the Linux RDMA subsystem with some user space update, and finally a summary. So to put it simple, RDMA can be simply said as a DMA plus network. So the NIC is in the central role of this RDMA stuff. So the NIC is in charge of doing DMA operation from the RAN or to the RAN, and then receiving the packet to the network from the network. So as an example for the RDMA write operation, the initiate side, the NIC will do a DMA read from the memory and sending the packet to the network. But the responder, the NIC will receive the packet from the network and doing DMA write to the memory. So because this involves a DMA operation itself requires some proper setup of the memory. For example, for the application side, it passes the virtual address to the RDMA API, but the hardware doing the DMA operation require the bus address, sometimes we call DMA address here. In order to do that, the NIC has internally maintained a page table, so it can do the virtual address to DMA address translation. In order for this scheme to work, the memory pages has to be pinned, or alternatively, the NIC need to support on-demand paging, so it can update the page table dynamically if a page fault happens. So the initial setup for this DMA and the page table setup require a procedure called a memory registration. If the user buffer is in system memory, the memory registration time, the driver will call get user pages and the DMA map SG, this kind of function to translate the virtual address into the physical address, so it can be used as a DMA operation. However, if the memory is in GPU, the story is a little bit different, because the GPU memory are mostly local to the device itself. They are memory mapped to the I/O space, so they are outside the normal regular memory mapping of the system. Those memory doesn't have the corresponding structure page, and the get user pages and the DMA map SG don't work correctly for them. So the NIC driver cannot use the same way as the system memory handling to deal with the GPU memory. It need to find some different way to communicate with the GPU driver to get the necessary information in order to set up the internal page table. There are existing some solutions like GPU Direct that has been there for a long time and has been working quite well. The only issue is this is only available in MOFAD. So if we want some upstream solution, it's not there. So here we present our solution to use the DMA buff as the mechanism to communicating between the GPU and the NIC to deliver the DMA address information of the buff. So DMA buff is a standard mechanism in the kernel for sharing buffers between different device drivers for the purpose of DMA usage. In the concept of DMA buff, the owner of the buff is called exporter. So the exporter will export the shared buff as a DMA buff object. At the time of the exporting, the exporter will define a set of operations that can be applied on the buffer. And those operations will be called by the DMA Buff API by the importer. And the exported DMA buff will be associated with a file descriptor. That file descriptor is passed up to the application in the user space. The user space application can then pass the file descriptor to the site that want to use the buffer. That is called the importer. And the importer will then call the DMA Buff API function to import the object based from the file descriptor, and then get the address mapping for the buffer. So by doing this, it doesn't need anything to deal with the struct page. From the exporter side, the DMA Buff API is quite simple. It basically only have two functions. The first is a DMA Buff Export, is to export the buffer as a DMA Buff object. At the time of exporting, the exporter has to define the set of functions. It's shown at right-hand side of screen. Only a few functions are mandatory, actually related to the DMA operations. There are some other functions like the mmap, CPU access. Those things are for CPU access, so not very related to the DMA operation we discussed here. The second function for the exporter side is the DMA buff FD. That's to associate the buff with the file descriptor. From the importer side, the functions there are four types of functions. The first one is to retrieve the object. So this is the get and the put operations. And then there's a function to attach the device to the DMA buff. So the device itself is the user. So that is going to do the DMA operation. The exporter operation at this point will determine if the DMA device is compatible with the buff. I mean, the buff can support the DMA request from the attached device. Mostly they will check the distance if they are in the PCI subsystem, how they are located each other, are they accessible, especially with regarding to the peer-to-peer access. And the third class of function is the mapping the address. So DMA buff map attachment, that one will translate the virtual address of the DMA buff itself into a list of DMA address and return that to the importer. And the fourth class is the CPU access that are listed in the right-hand side of the screen. In this API, there's one thing you need to notice is about the type of attachment of the importer to the DMA buffer. So the attach can be static or can be dynamic. For static attach, the buffer is pinned to the memory. That the page is fixed. So the GPU driver, the problem is the GPU driver, they usually don't allow pinning device memory. So when you try to do a static attach, the GPU driver, it will actually move the buffer to system memory. So that is not really what we want for DMA operation. For dynamic attach, the buffer is not pinned. Instead, the importer will need to provide a callback function. So that function is called whenever the buffer is moved to a different place. So this attach style allow different device memory access, but it requires more work from the importer side, but it is preferred by the RDMA usage. So here's a workflow on how the RDMA system work with the GPU driver using the DMA buff. So the entire thing, most of those things happen at the memory registration time. Once the memory registration is done, the RDMA driver can work mostly similar to what the regular memory is, except some details. From the GPU side, so basically the GPU driver has internally have the DMA buff support. It has all the functionality needed to export DMA buff and expose the interface to the user space through some device interface. The GPU library will access the GPU driver, allocate a memory, getting the file descriptor. That information passed to the application. The application get this file descriptor and also get information about the offset of the buffer that is going to be used for the RDMA operation, because it could be not the entire DMA buff, it could be just a subset of DMA buff, and all the size information. All those informations pass to the various level of user space library. In the picture, we show the OFI and the RDMA library, and then passing to the RDMA driver in the kernel space. The RDMA driver will import the DMA buff and setting up the NIC, and finally the NIC will do peer-to-peer DMA transaction with the GPU memory. Here's a summary of the user space DMA buff allocation method currently available. So many of the GPU drivers support the DMA buff allocation as a part of the DRM, the germ, and prime interface. Those are accessed by IO control over the DRI render interface. Here's a list of the IO control command that for different GPU drivers. So all those can allocate some DMA buff and convert the handle to the file descriptor. Specific GPU libraries, they may provide a higher level abstraction over the IO control interface. For example, the one API level 0 has the DMA buff allocation capability in the memory allocate device in API call, and the memory get allocation properties is able to retrieve the file descriptor, and the get address ranges is able to get the starting address of the DMA buff, so the application can calculate the offset is going to be used for the memory registration. And also the get IPC handle is a different way to get in the file descriptor. So in order to support this RDMA operation with the DMA buff, we need to make some changes to the RDMA driver. The changes can be, I mean, we need some changes in the core driver and need some changes to the device driver. For the core driver, at first we add some common functions for importing DMA buff and doing the memory mapping. Those are similar to the importing function, similar to the regular IBUM get function, but with the additional parameter like a file descriptor, and also the attachment ops that has the necessary information for attaching the device to the DMA buff. The map page function is wrapped around the DMA buff course to mapping the DMA buff object, retrieve the DMA address list. Those functions are called by the device drivers to do the actual operation. In the core driver, we also need to add a new verbs command for the memory registration, because this registration requires additional parameter. So regular IGMR function does not, is not suitable. For the same reason, a new device method is added to the IB device structure. The vendor driver, I mean, for the specific device, for the specific hardware, also needs some changes. At first, it has to implement the new device method, user MRDMA buff, and then it has to implement the callback functions for DMA buff move notification. So in the callback functions, it has to invalidate the corresponding entries in the page table. And the callback function is passed up to the IBUM DMA buff get function through the ops parameter. The vendor driver also need to handle the page fault related to DMA buff. So when the DMA buff moves, the page table entries is invalidated, and if any transaction involving those changes will cause a page fault, and we need to define a specific page fault for this situation. And in the page fault handler, it will call the previous defined the common mapping function to get the current mapping, and also update the page table so the operation can continue. So it is apparent that on-demand paging support is necessary for this scheme to work. Yeah. The user space library also needs some changes in order to work with the kernel, the new kernel functions. So we have 3 changes made to the libIB verbs. The first one is we need to add a new API function. That is the first one here. IBV regist DMA buff MR that had an additional parameter, the file descriptor here. And also we use offset here instead of the virtual address. The second change is add a new uverbs command from the user space. That is number 3 here. And this is to talk to the kernel driver has matching the corresponding uverbs command inside the kernel. And the third, the provider of specific hardware need to implement a new method. So because the control flow of the user space libIv verbs is going through 1, 2, 3. I mean the API function calling to the provider specific method, and that method is in turn calling the verbs command function. There are other user space changes we made to the RDMA core. For the providers, it implemented that specific method. And also we made some changes to the PyVerbs and the test to support the new added functions. At the higher level, we want to enable Dma Buff in some middleware. One example is the OFI. So for FI, the FI-MR attribute structure has space for device memory. It has the interface argument to distinguish between different API for memory allocation. So APIs that use Dma Buff will be presented as a certain type. And for those type, the file descriptor is available as a parameter in this structure. And the provider needed to recognize those fields and handle the registration properly by calling the new verbs functions. So this capability is indicated by a special bit. Application can use this new interface explicitly for optimal performance, but also for the OFI, there's a way to support this implicitly by using something we call the hooking providers. So the hooking provider, we automatically detect the memory type based on the address and register the memory accordingly. Each hooking provider will only handle one interface type. So for the UCX, it only took some very quick look on what things need to do to enable Dma Buff in UCX. So I took a look at the Rdma Transport. There are two possible approaches to enable this. One is to expand the memory registration API. So we need to add in some actual parameters for extended memory region attributes as a way to passing the file descriptor down. And also some new flags, so to indicate something Dma Buff specific thing. That is the one approach. The other approach is do some auto detection. So inside the UCTI BMD regist memory region, it's possible to do something similar to OFI to auto detect if the memory address is actually belong to, the type is something related to Dma Buff, and then calling the proper function to the memory registration. So this auto detection can possibly be implemented as a service in the UCS. Just some rough idea on that. And either way, there are some actual handling involved with the local copying, involved the device memory that need to be handled separately, like what the CUDA and the other GPU API does. And also the other aspect of the UCX need attention outside of the RDMA transport that may need some new addition or changes in order to handle DMA buff. So those are details I have not been looking into yet. Yeah, but those things are, yeah, there are definitely something need to be done there. Okay, in summary, DMA buff provide a very viable mechanism to support the GPU RDMA, and there is a potential to get this into the upstream. So we have a software implementation completed and right now under review. Here's a link for both the kernel patch and the user space patch. These are based on kernel 5.10 RC1 and the most recent RDMA core. We have validated with upstream AMD driver and then Mellanox 5 IB driver and the internal i9515 driver. So we will continue to work on getting the upstream acceptance and also working on the enabling software ecosystem. So any comments or questions?
I would certainly love to hear from the AMD people. I think I saw on this call if this is also what they are going to be able to use in UCX with ROCm.
So I think the IB like the IB driver should work fine with the ROCm stack as far as I could tell. But I would like to read it up a bit more detail before commenting on that.
Okay, did you have some specific details you were interested in?
You mean this part or the earlier part?
So the memory registration, as far as I know, works similarly between CUDA and for CUDA and ROCm GPUs. But
does it
yeah,
work similarly? I don't actually have very little idea how.
Yeah, for CUDA and the ROCm, I mean they're using the GPU Direct protocol. Yeah. I mean, both have the drive, the hooking. I mean, the plugin for the GPU side talking to the GPU Direct mechanism on the RDMA side. Yeah, in that case, in that sense, they're similar, and they just use the passing the address there. There's no actual parameter needed, so that's different from how the DMA buff works. Yeah, but the downside is only works. I mean, it doesn't work with upstream kernel.
So the thing that's closest to the pure direct out of tree thing would be some version of this that could get the DMA buff from the VMA. That would closely match the semantics that I think NVIDIA and AMD are both implementing too right now.
Yeah, I actually wanted to comment on that. What is the basic reason that we need to pass around this file descriptor, especially for every buffer? Can't we, like Jason said, get everything from the VMA, and every exporter would attach the operations to the VMA?
That's a good question. Yeah, actually, I am not sure. I mean, so do you mean the DMA buff is actually available, always available? When
let's say that you want to, as a NIC implementer, for example, you want to pin some memory. You would normally go to VMA and or maybe just do get user pages and expect to get struct page. But let's say that instead of that, we would take the virtual address, we would find the corresponding VMA and check some flags or type or operations on that VMA, which tells you whether you can use get user pages when you have a set of operations on the VMA, which is probably the same operations that you described for DMA buff, and you would use these operations instead of get user pages. Maybe we can even take this one step further and expose a DMA buff-like operations for a host memory. Instead of implementing both get user pages path and the DMA buff path, maybe we want to create DMA buff would be always the intermediate layer between NIC and memory. So we don't have to implement the same thing twice.
Yeah, that's like some good information. I mean, yeah, for me, I actually didn't realize the file descriptor is actually available in this way. Yeah, probably I need to take a little bit of further look into that side if that's some viable way doing that way.
Well, it isn't actually available today. There's a lot of technical problems there. Apparently, that the VMAs are attached to the wrong file descriptor, basically, when the drivers create them, and I don't know if that can be fixed easily. Daniel suggested it was not an easy fix.
Maybe we can attach DMA mapping operations to a VMA or get user pages operations to VMA.
Yeah, I think that was suggested as like the shortest path is to add a new VMA ops to convert a VMA to a DMA buff.
Yeah.
I'm not sure if that's politically feasible, but I was kind of imagining once we get this part done, then it's a good consumer of that interface and maybe it could be discussed.
Also, as a general comment, we had some discussions recently on this. We need to make sure that all the APIs would work efficiently with compound pages, in the sense that if it is possible and the pages are physically contiguous, we could implement a return or something like that, a relatively small number of descriptors, or pass around small number of descriptors between the importer and exporter.
Yes, the RDMA side of that is complete. The requirement is that the DMA Buff Exporter has to optimize the scatter list to join physically contiguous pages. So I don't know if the drivers do that, but that's what they're supposed to. That's what they need to do.
The GPU side, they export the RDMA list return is actually quite optimal. I mean, they are as contiguous as possible. I mean, the thing is at the importer side, because the buffer can move. I mean, every time they move, it can change. So to really use that continuity is a challenging thing to do.
Well, that's a driver detail now. So the issue you'll see is that you have to assume that it could be moved to a place where there's no contiguity. So you have to have the ability to go to 4K pages.
So migration callback should also include split?
Well, you need to, it's kind of a rereg MR problem. You need to be able to pause an M key or an L key, or well, an L and an R key. You need to be able to pause it and then reconfigure the translation completely, including page size, and then resume it, is what the driver needs to be able to provide.
So meaning that the API that we described in the one of the slides, which tells you that memory has moved, should actually be two callbacks, like one the memory started moving and some kind of.
Yeah, it's structured like that internally, essentially.
Yeah, but for the callback, we actually don't need that one, because internally there's a locking mechanism there. So when the moving finishes, I mean, because when you're trying to do the mapping, it will waiting on that lock. So.
Yeah, I remember it was a relatively tricky part with ODP, all that locking while you have memory notification handler.
the memory notification, and then we involve the callback. The callback function just do the invalidation and then return. And the exporter will continue the moving operation. And then when it is done, it will release a lock.
And
Only
a lot
after only after release the lock, the importer can remap the pages again.
Until then, the process, let's say, if it's host memory, the user process has to be suspended. So
I mean, the RDMA operations, if there's a waiting, because the invalidation happens, when the invalidation happens, if there's an ongoing RDMA operation, that one will be paused. The user it's actually not directly related to the user process here. Is the on-demand paging stuff. Basically the RDMA, if there's no RDMA operation happening, all these things are happening in the background, like in the driver. It's not really affecting any user process.
Well, we don't have a very good optimization there because we still invalidate the MLX5 implementation still invalidates the M key every time
if
it
the
migrates, right?
If the M key can reuse at this point, like you said, they pause and update the things.
We will keep on getting page faults, I guess, until we actually resume or finish mapping the new memory. At least from the MLX5 side, we can.
Yes, it's possible. But the real testing seems to be just working fine. It's not that we don't see a strange performance behavior there.
Yeah, I think it also can be tricky if we want to handle both ODP case and non-ODP case in DMA buff. Because if for example, we say that our preferred method is dynamic, it means that we always have to use ODP flows. We would mean that we will have maybe less efficient data structures or smaller page size because we always assume that we could have ODP events. Kind of would be less optimal. What do you think, Jason? If we use ODP, does it mean we have to always do 4K?
This is getting really into the details, but I think on MLX5 we can do dynamic page size changes with ODP, specifically for DMA buff, with the proviso that we have to over allocate the pass list.
Yeah.
So the implementation is a bit complicated, but you basically you start out with a 4K pass list, and when you want to load it with something, you figure out the page size, you'd set the page size and load it with that page size worth of data, the data formatted in that page size, and then invalidation has to go kind of through that whole cycle again. So you'd get the hardware optimality of being able to cache large pages, but you don't get the optimality of having minimum memory footprint.
Either way, those are, I think they are future improve room for that side. I think.
Yeah, there's definitely a path to at least get the performance to be the same, to be equivalent to what the peer memory API has with large pages.
What do you think about using the same APIs also for host memory? Because if the API is really good, then why should we have separate flows for host and GPU memory in IB?
Because the API is not very good. I don't think you want to go through the extra step to make a file descriptor for every piece of host memory you want to do DMA from, and then on top of that create an MR object. It seems extremely wasteful. And DMA buff forces you into the ODP flow, which is again, kind of wasteful if we really wanted a pinned memory.
Yeah,
MK.
but then it means that for every registration in MLX5, we would have to implement our ODP and registration both on top of DMA buff and on top of a regular host memory.
DMA buff
No,
flow is completely different code. It's like a,
yeah.
there's 3 completely different code flows in MLX5. There's now with the patches, there's DMA buff, then there's ODP, which is completely orthogonal, and then the pin memory case.
Yeah, but sounds like it's like not the optimal way to
No,
do
it actually
things.
is. This actually is kind of the optimal thing because they all have different restrictions and different rules and different control flows. The DMA buff really doesn't share anything with the ODP flow that's based on HMM.
Okay, but isn't it like kind of the same like host memory, that you have memory, doesn't matter where it is, and you're able to pin it, and you have some operations to convert it to scatter list.
I mean, yeah, sure, at a very, very high level, yes, but all the details are different.
Yeah, I mean, for example, it doesn't use the gather me user pages, so that's different from the host memory, and it doesn't use the actual ODP, the page-based. I mean, those updating flows. I mean, it only use the capability to handle page fault to do the invalidation. Only these 2 parts are similar to what the ODP does. Otherwise, it's totally different from the ODP flow. And when the page fault happens, it loads the entire Dma buff, updating all the mapping. So it doesn't need to do update the mapping page by page.
Yeah, we're trying to get to that too with ODP, but it would be a completely different API. It would be HMM based. Like, no, I don't think there's any commonality here. I've actually been spending a lot of time in the last year splitting these 3 flows up, well, the 2 flows, so that they're not trying to share code because it was just a mass sharing code that wasn't actually the same.
Okay.
The question I think for kind of the UCX world is how do you fit this extra file descriptor into the memory type
But
cache and all
hopefully
these
it would
other.
go away if you could put everything on the VMA. How final is that approach of using file descriptor?
Well, it'll definitely happen. It looks like. The question is how likely is it to be able to use the VMA, and this I can't predict. It's more of a.
I think
kind
in
of a
UCX we
GPU.
would need to use. I mean, putting aside for a second the fact that we would need to create a buffer, sorry, file descriptor for every buffer, and the limit that we have on number of file descriptors and so on.
Yeah.
Sounds like we would need to have a VMA like structure in UCX and cache per process all the file descriptors that we have, like essentially duplicating the logic that we already have in the kernel.
Yep, that's right.
Wait, has anyone really thought about the file descriptor limit? Because that tends to be a really harsh limit. Like, isn't it like 1024 or something? Unless you change it.
You can bump it up with some.
You can bump it up, but that doesn't happen a lot of times for customers.
No, people doing this will have to bump it up. There's also a VMA limit, which I assume people doing this kind of stuff are bumping up as well.
But you don't have a
That one hurts
CUDA
too,
buffer
yeah.
per VMA. Yeah, you can have many CUDA buffers per VMA, but here it sounds like we need file descriptor for every CUDA buffer.
Well, it would be, like you said, it would be for every VMA. So somebody somewheres would have to figure out, what the VMA was and get the buffer for it, get the FD handle for it. Either.
You mean that we need to somehow, let's say that we're in UCX, we're not aware of VMAs. We're only aware of buffer pointers that the user passes, let's say, from MPI.
Right, but as soon as you get, the first time you get a DMA buff, you'll be able to extend it, I think. And from that, you can kind of compute what its VMA was. It's horrible. The whole thing is horrible. Wow.
and give the file descriptor limit. Maybe not everyone could extend it because sometimes users don't have permissions to increase their limits, and obviously we don't want to spend a lot of kernel file descriptor structures for small buffers.
The other way, the memory allocator has the potential to like allocate a big memory for with a single file descriptor and returning to the user means separate chunks there.
The problem is that memory allocation usually happens outside of UCX library. It could happen just by application calling some CUDA malloc function, or it could happen by memory manager like RMM or like any other method that you would use. And in UCX, we just get the buffer and the pointer to that buffer. And if you need to some way to figure out the VMA, hopefully by not by parsing some files in procfs, and then out of that extract file descriptor, all adds overheads.
Yeah, the clear winner here is to have the kernel do it all.
And only during registration time.
Yeah, there's still some problems with that. Like we can't cross VMAs in the kernel either. So your buffer that you want to register has to be a single, a single DMA buff. We can't. I don't know how we could combine 2 or 3 of them, for instance, into an MR. But
can you
maybe
cross VMAs in a regular host memory pinning?
Yeah, regular host memory has no restrictions. But when we move in these special paths, well, it's particularly the DMA buff special path, it's all a big mess.
Well, and maybe you could pin pages, allocate some of each VM of every VMA. In theory, you could do it if you write like really complex logic on the importer.
Yeah, I think that's not likely. I would prefer to see an HMM approach instead of messing around with DMA buff in that kind of scenario.
HMM plus mlock, for example, if we really need to fix the location.
I don't know. Maybe that's sort of getting back to the micro optimizing. But HMM lets you learn the P2P pages theoretically, and it doesn't have these weird restrictions on requiring file descriptors or VMA alignments. It just sort of works theoretically.
So
I guess I wouldn't say this is
you.
the final word in how to do this upstream, but it is a good step and it's a good option for at least some workloads.
Okay, thank you, Jianxin. Appreciate it.
All right, thanks.